Hi, I'm Matt Turner, and welcome to part 2 of my videos on the Unix file system, including the Linux and OS X file systems. So in part 1 we covered off kind of what the file system is, what individual file systems are, how you build up that namespace, that hierarchy of paths and file names by mounting file systems on top of each other, and we looked at how files are actually just links to inodes and how the inodes hold the metadata about the file and a link to all of the actual data stored on disk, and how that inode abstraction gives the Unix file system a bunch of power and a bunch of features not seen in systems on, for example, Windows. Here today in part 2, I'm just going to dive over a couple more details, various facets of the file system and things that come up when you look at this. So first of all, I want to talk about the various file types. The kind of file, in quotes, that you're familiar with, normal file as it were, is what's called a regular file. So this is really a file that holds any data, and that can be a very wide range of sins, right? This data can be can just be unstructured text. It can be random, non-printable binary characters. It can have a structure like a JSON or YAML or Word document. It can be a binary and an executable, and actually those files have formats themselves, something like ELF or COF. But anyway, that's, a regular file covers a very large range of things, but basically this is where you use the file system as a data store, right? So this is a bunch of data stored on disk that I want to sort of persist. But it's not the only type of file. It's not the only type of thing that a file name, an entry in a directory, can point to. The next type of file that you will be familiar with but may not have realized is quite as similar is a directory. So logically, this is a directory is a list of names, a list of file names, so just the end part, just the leaf part, and the corresponding inode numbers for the actual files that are represented by those names, that are linked to by those names. A directory is actually just a name, a link to an inode, and then that inode links to one or more blocks of data on the disk, just like a regular file. But having the directory sort of bit set on the metadata says that this file should be interpreted especially, read as a directory listing, not read as a document. That on-disk layout is actually specific to each individual file system, but the general principle is that the directory bit says that any particular file is a directory, and whatever file system it's part of should be asked to go and read that block of data on disk, and it should return a bunch of kernel data structures representing the files in the directory, rather than like a string of bytes, which is like a regular data file. Symlinks, like I said in part 1, again are just a name pointing to an inode, pointing to some data. That data are again interpreted specifically, so the file is expected to contain a path, relative or absolute, and that is then used to go and find another file. Remember, hard links are multiple names pointing to the same inode, but because they're based on inode numbers, they have to stay within one file system. A symlink lets you point anywhere. There's no guarantee that the file on the other end existed when you made the symlink. There's no guarantee that it exists now. They don't reference count the files that they point at, but nonetheless they are a very useful mechanism for installing links across file systems. And symlinks are very obvious, right? They display in ls in a different way. They have the link, the L right on the left, because they have that link type which is displayed. Whereas unless you sort of peer closely at the hard link number, hard links are a lot harder to spot. So symlinks do have a lot of uses. Now things are going to get more interesting. So the next type of file is a named pipe. So you'll probably be familiar with pipes made by the shell, like in this command we can see here, cat foo.txt and pipe to tail. So in this case, bash makes a pipe when it runs these two commands. It runs cat, it runs tail, it makes a pipe, it connects the output of cat to the pipe, and it connects the output of the pipe to tail. And this pipe only lives as long as the processes that are using it and it's sort of unnamed, right? It has no name and no namespace. There's no namespace in which you can look it up. There's no way for other processes other than cat and tail, to which Bash has attached this pipe. There's no way for other processes to find it, connect to it, start using it. It's kind of hidden in this little shell pipeline. So maybe you do want a pipe that lives longer than other processes. I want this cat to be able to finish, and then a different cat of a different file to come along and be able to connect to the same pipe and start sending more data into tail. There's many reasons why I might want that pipe to live longer. Or maybe I want the pipe to connect to processes that can't be started with one shell command like this, right? Maybe one starts way before the other. Maybe they have to run as different Unix users. So for whatever reason, I can't get Bash to make myself this anonymous pipe. And because this pipe is anonymous, the two processes that are going to use it have to connect to it sort of when it's made, because otherwise any reference to it is lost. So for whatever reason, if I want a long-lived pipe or a pipe that I can actually find and discover and use after the fact, after it's been initially made, I can make a long-lived pipe and expose it as a name in the file system. So I can give a name, say my pipe, in a directory like run, and I can have that be a way of discovering and opening and reading and writing from a pipe. And I can even make a pipe sort of anchored in the file system, rather than making a pipe like the one above with two processes connected to it straight away. I can make a pipe that's nothing's using, and it can hang around a bit until things come along and start using it. And the make FIFO command does that. The next are sockets, Unix domain sockets. So these are sockets that have been made and exposed by the file system, kind of like those pipes. So the address space for these sockets is the Unix file system, as you can see here, via run foo.sock, rather than IP addresses and ports. So if I want to connect to this socket, you say something is listening on this socket and giving responses, returning HTTP. The way I connect to this is not to connect to 1.2.3.4:80. The way I connect to this is to connect to via run foo.sock. It's a name from the file system namespace rather than the TCP namespace. And these things they're kind of like pipes on steroids, so they're full duplex, whereas pipes are simplex. And the sockets use the networking stack code in the kernel. So these sockets can implement TCP or SCTP or UDP semantics. Right, so two processes can connect to each other via this socket, and I can get reliable in-order transmission, I can get unreliable out-of-order transmission like UDP, I can get whatever by leveraging that networking code in the kernel, and pipes can't do any of that kind of stuff. So again, I could have two processes, and they could use this socket to communicate. So they could communicate over the loopback interface, right? One could listen on 127.0.0.1, port 80, and the other one could connect to it. The problem with that is there's only a finite number of ports on that loopback interface, so I could run out. And these two processes would have to coordinate with all the other processes in the system that want to use loopback and broker port numbers, make sure they're never going to clash. I can put my name socket anywhere I like. I can come up with any arbitrarily complicated path in the file system, put my name socket there, and of course I can also use Unix file permissions to restrict access to it, because the name points to an inode, and that's got all the standard Unix metadata, along with information about who owns it, when it was made, when it was last modified, that kind of thing. The last two types of device are often, the two types of files, are often clumped together, and they're called device files. So device files are files which represent hardware devices. So the file system in a Unix system is pretty pervasive. You may have heard the phrase everything is a file, which I'm actually going to talk about in a minute. But discovery of the hardware in a system and access to those devices is mediated by exposing them through the file system. So again, this way, with a file representing a hardware device, ownership can be set, access can be restricted with file permissions, whatever, and then ls on the directory full of these things can be used to find what hardware I've actually got in the system that I might want to access. So block and character devices both do that. They're a little bit different in their semantics. I think this is a common misunderstanding. Most people think that character devices can only read or write 1 byte at a time, because that's the size of the sort of character type in data type in C. That's not actually entirely true. The difference is buffering. So a character device is often serial only. That is, if the underlying device only sort of can really read from start to finish, like a tape, that's all the character device representing it can do. They're not, I can't do random access because the access is unbuffered by the kernel. The access is direct from whatever process is using this down to the device. So you may often have like a raw disk device for your hard disks, which is typed as a character device. So you see like /dev/rdisk1 or whatever. That's a character device. That doesn't necessarily have a block size of 1. It can have a block size that's not 1. If it's a disk, it'll have a block size of 512 or these days 4K. But the thing is, it'll only allow accesses of reads and writes of exactly that size, and they have to be correctly aligned on a 512 byte boundary. There's no buffering. There's no unaligned access is allowed. Often, though, random order access is allowed because there's nothing in the way between this process that's trying to access this device and the device itself. Block devices, on the other hand, are buffered by the kernel. That's actually the big difference. So that means that whatever block size you want to use, whatever buffer size you want to use to access the device is decoupled from the device. You can do random access at different places in the device, all over the place. And as I say, you can use the arbitrarily sized buffers, and they can be unaligned. And then the kernel has code to do to work out which underlying blocks you're going to touch, and to do read, modify, write loops for the ones that you're sort of only partially touching. So you are decoupled. You can believe a block device has any buffer size you want, and you're decoupled from the underlying block device of the block size of the hardware. That's actually the difference between character and block devices. Obviously, block devices therefore are a little slower because there's that abstraction in the way. There's some copying. There's some buffer management. If your buffer that you're trying to use only touches part of a real block underneath because of the alignment, then you're going to have to do like a read, modify, write. Your random access into a tape drive, it may be very well to say, I want to read a kilobyte at 3 megabytes into this device, and then I want to read a kilobyte at 2 megabytes in, but that may well involve, the actual device winding the tape from the beginning up to 3 megabytes, reading a K, rewinding all the way back because it has to dead reckon, and then winding forwards another 2 meg to find yet another kilobyte. So although the block device abstraction will let you do that, it can, potentially be very, very slow. So the next thing and the last thing I want to talk about in this video, and this is going to get a little bit philosophical, is a quote you may have heard saying everything is a file. So we've talked a lot about the Unix file system and how the file system is this namespace of names that I can use to get various things, regular files containing byte streams of data, directories of symlinks, which is sort of metadata to arrange those files, and then also the sort of Unix philosophy of exposing other things like pipes and sockets and hardware into the file system as a way of discovering them and interacting with them. So you may have heard that everything is a file. I think that's not actually entirely true. That's a little bit misleading. I think it's more accurate to say, well, everything is a file, but a file is a stream of bytes. So I think it would be a more accurate statement to say everything is a stream of bytes. That is, there is a common API for interacting with a lot of different types of things on a Unix system. So if I open and then start reading from a file, on a disk, an actual file that exists, or if I open and start reading from a file in a virtual file system that we'll see soon, that's actually be generating on the fly, or if I connect to a TCP socket on a server on the other side of the internet, or if I start opening a raw hardware device, all of these things have the same API because they all look like a stream of bytes. They can all be opened and read and potentially written and closed. Right, and so I can use select, if anybody's familiar with that. Select is a system call that I give a bunch of different file handles to, and it goes to sleep until one of them's ready. So it lets me hold, a bunch of different files open and say, as soon as one of them has new data in that's ready to be read, wake me up. So I can select on files and sockets and pipes and signals and all these different data sources all at once using, all together in one system call using this one API. And as soon as any of them says they're ready to do anything, I use the same read call to go and get that data from them. And that's just, that's just an opaque stream of bytes. I have to know what this device is, what this file is, what I'm getting from it, how to interpret it. But I can use that simple low-level API to slurp opaque bytes in, to write them out, to pass them off wherever they need to go. Compare this to, say, a system like Windows, where there's about 15 different system calls for reading. If I want to read from the network, from a network socket, it's a different system call to the one for reading, signals, or reading GUI events, or reading files, or reading something else. But in Unix, all of those things are sort of presented to me as a stream of bytes. So therefore, I have this one unifying API over them. And I think that's what's really meant by everything is a file in Unix, right? If I want to get information about a running process, I open various files that we'll see in /proc. If I want to read from a network, I get a file descriptor, I call read, I give it 4 kilobyte buffer at a time, and I get the data. It blocks when there's no more data, just like a read to a file blocks when I reach the end of the file. What people, I think, usually mean when they say everything is a file is that everything has a file name, and that's not true. Some things have file names. So like I said, when I connect to 1.2.3.4 port 80, I get a stream of bytes, and I can read them, and I can write them maybe, and I can select them. When there aren't any more bytes, read blocks. That's my standard API. It's got a standard syntax. It's got standard semantics. But let's say, how do I know what machines and what ports I can connect to? Would it make sense to have a sort of /net directory full of all the possible IP ports and pairs that I can connect to? It wouldn't, right? It's kind of pointless for discovery, because I know all the possible IP addresses that could exist. I know all the possible port numbers. They have a very well-defined format. I can generate all of them. My system, so let's say I generated a directory, a /net directory full of all of them. Well, for a start, there'd be 280 trillion. And that's only TCP. That's before we have UDP ports or anything else. So in terms of discovery, I can generate all of these addresses and ports. I know what they're going to be. It might be useful for me to know which ones I could connect to now, which ones are up and open and listening, but my system can't realistically go and, ping all 280 trillion of them every second and remove the files for the ones that aren't currently ready. So as a sort of discovery, availability mechanism, it's pointless. When I want to connect to an IP and a port, I just have to kind of know what they are. So I just call connect, which is a different system call. It's not open. And I give it the IP and the port without without a path prefix, without a qualification, without that /net that would sort of say it's special and it's part of the network. Because I'm calling connect rather than open, I know what I'm giving the address of a TCP socket and not a file. What gets returned is a file description, right? What gets returned is a file handle that talks the standard read, write, select, close API. But what I'm saying is that it doesn't make sense. So sockets, network sockets are a file, but they do not have a file name in the file system, because that doesn't really make sense. For a lot of other things, it does. Not least from a sort of discovery point of view of the various files that I could open. So as I say, I can get a bunch of information about the running processes on my Linux system. There isn't a special API for that. There isn't a system call that's like get running processes and then read running process information or anything. I think there is on Windows. On Linux, all I do is there's just a special place in the file system. So I just open read, write, select /proc /process ID /something else. So in this case, not only are those things files, those tables of information about the process, they're not magical data structures returned by a magical special system call API. They're just streams of bytes, and I have to know how to interpret them. So they are files, and they are also file names, because I can ls in /proc, and I can see the set of process IDs for the processes that are running at the moment. That set is reasonably sized, so I can ls it without my computer exploding. There's not 280 trillion of them. And it's changing, so I can run that ls at different times, and I can see the different sets of processes currently running, and that is useful information in itself. So yeah, in that case, I would just call open with a path that's under proc. So this is, this kind of file system interface to lots of different types of information is great, because it makes that addressing consistent. I know that /proc is processes, /sys is system information, etc., etc. /dev is the device files that we were talking about, that way of exposing hardware devices into the file system, so I can find them and interact with them in a standard way. And that allows for me to have this one common API, open, close, read, and write, to use for data manipulation and transfer and processing. And everything, a lot of things are text. You can make heavy use of pipelines that we've talked about. So especially if you like sed and awk, you can perform manipulation and filtering and transformations on all kinds of different data, or obviously you can write custom code to do it. So yeah, with that in mind, I think almost everything in Unix is a file. Some of those things are, are paths. Some of those things have file names. Some of them don't, and you sort of discover them and access them and open them in a different way. But then you do still get a file descriptor and this standard file abstraction. So having said that some things have file names, we'll just give a very quick tour here at the end of a few of the different virtual file systems that exist. So if you remember all the way back to part 1, I showed that I had a system, it had a disk with an actual blobs of data on, the actual distribution that we were booted from, and that was mounted at /. But over the proc directory was mounted this thing called procfs. This is a file system, I can ls into proc and I get a bunch of directories named after a bunch of numbers. Those don't actually exist on a disk anywhere, they don't persist, they're not stored. They're made up on the fly, and there's one of those for each of the running processes in the system. And if I ls proc1, because every system has a process 1, I can see a whole bunch of files and directories here that represent different pieces of data and metadata about this process. So yeah, as I say, this is my API on a Linux system for getting information about running processes. It's not some weird special system call, some special side channel I have to know the design of. It's all just exposed into the file system. And the way that happens is through a special file system called proc, which goes and does that for me. I mean, obviously under the hood it is actually making system calls, right? I couldn't tell you quite what they are. Well, it runs in kernel space, so it's probably directly accessing the data structures. It's probably not making any sort of user accessible system calls. I imagine it's making internal kernel calls and poking internal kernel data structures. But don't quote me on the actual implementation of that. So in this case, I can list proc1 and I get a bunch of different files that'll tell me a bunch of things about process 1. So drilling into some of them, I find out that there's a file called exe in every process's directory. That's a symlink that points to the actual binary that's running. So process 1 is the init system. On a modern Linux system, that's very likely to be systemd. So process 1, the executable here, the thing that was actually run to create process ID 1 was libsystemd. So proc1 exe is a link, it's a symlink. You can see from the L on the very left hand side that points to libsystemd. I can cat proc1 command line. That's a regular file. It contains the arguments passed to this program. The program always has its own name as argv0. That's a different discussion. But this thing's also been given the -- system to tell it it's the systemd rather than the user one, and then -- deserialize and the number 47. And I have no idea why or what those mean. There's also a regular file called environ, which is generated. It's a key value pair. It's generated from the environment of the running process. I've trimmed this down a bit, but essentially that system level systemd is running under the following Unix environment. There's another file system called sysfs, which is mounted at /sys. Gives you information about the system and the ability, so I can tune a bunch of kernel parameters through this. Also, one of the things it gives me is this device directory through which I can actually do sort of hardware discovery. So in here I can list, I can get a very hierarchical view, and here I'm listing function 0 of device 0 on PCI bus 0. And I probably missed a couple of levels of the taxonomy in there. But sysdevice is PCI whatever is sort of the very first device on the very first PCI bus in this system, and there's various files in there that give me information about it. So vendor is the hex code for the vendor, so the manufacturer of this device. Device is the code for the whatever actual piece of hardware it is made by that vendor. You can see here the vendor ID is hex 8086. That's a nice little industry in-joke. Obviously, an 8086 was an early processor by Intel Corporation. So vendor hexadecimal 8086 is Intel, and then device 1237 in hex. Actually, as it happens, means this is an Intel 440 Northbridge, right? Which is why it's the very first thing on this PCI bus. DevFS is what I was talking about earlier. DevFS is the file system that exposes hardware devices into the file system. So I know on a virtual machine that every virtual hard disk is going to be called VDA something. So I can ls dev VDA star, and I can see that there's one disk, VDA, and it's got 3 partitions in it, 1, 2, and 5. You can see from the B on the left-hand side that these are block devices, right? They're owned by user root, group disk. So these are files, special, block device files, special files that have exposed various parts of the hardware into this system. This was the kind of old addressing scheme. So the other thing to note in DevFS is that there can be several addressing schemes to get you to the same piece of hardware, several ways of naming the same piece of hardware. This sort of, VDA, where V means virtual disk and H means ATA hard disk and S means SCSI disk, and then, D means disk and A is the first disk, and then 1 is the first partition. All of this stuff is kind of arcane and it's an old naming scheme. It's it's preserved. But there's also a directory in DevFS called disk, so I can get at these disks by their path. In this case, where it's plugged into the PCI bus, right? So PCI bus 0, device 0, there's a controller 0, bus 0, device 4, I think is actually how you read that. So device 4, I guess, is the IDE controller. Function 0, the target 0 is going to be this first disk, and then part 1 is the first partition. So that addressing scheme exists as well. That's maybe more readable and more logical. But you can see that the implementation, what this virtual file system gives me, is a symlink to dev VDA. Same with by UUID, so I can access disks and partitions by their UUID, which is something that all modern partition tables and file systems give to disks and partitions. And you can see here that again there's a partition, in this case a file system with this long random UUID. And again, this is representing the same thing, so this is just a symlink back to that original dev VDA link. The one last thing worth mentioning is a system called Fuse, file system in user space. This is a way to write even more of those virtual file systems and write them easily. So Fuse lets you write a user space program. So if you wanted to implement a file system, you had to write code in kernel space. That's super hard to write, super hard to debug, very few programming features. It's just very long-winded code. Fuse is a library that lets you write your file system in user space, and it's factored out the common pieces of code that do the sort of minimal kernel interface. And all Fuse is a kernel file system, if you like, but it doesn't actually have any logic. All it does is call straight back out to a user space process. So this lets you write code that implements virtual file systems actually very easily. So you can add your own virtual file systems backed by whatever, just like procfs and sysfs and devfs. If you think about accessing things in the FTP namespace, right? Things on FTP servers. There used to be a CLI program for that called FTP. SMB client used to be the command line program that you use to get at Samba shares, CIFS shares, and you would run it, and it had a REPL, and you would give it magical commands and its own sort of addressing scheme for files. Now these things are just Fuse file systems. So now I can get at FTP, files over FTP or SMB or SSH, or even HTTP, with where I would previously use curl or wget, I can now mount a file system that mounts those things over parts of my my file system namespace. And people have really written Fuse file systems to do just about everything. Just about everything is exposed into the file system. Even things that I would argue, shouldn't be. Maybe they should be files, but they shouldn't necessarily have file names. That's a philosophical point of view. You can disagree with me or Linus Torvalds or whoever if you want. And you can use Fuse to really easily expose things into the file system. So that's all I want to say now. That got a bit philosophical. I hope it was interesting. The first part was quite practical. The rest got a bit hand-wavy. But hopefully this has given you some insight, in part 1 of this video as to how these things work, and in part 2 as to why they work the way they work, and the sort of overarching design pattern that the original authors of Unix and Linux were going for. So yeah, I hope you found this video useful. If you haven't watched part 1, there'll be a link in the description. Please subscribe. I'm going to do a bunch more videos on interesting but nerdy but interesting Unix topics. So check back. Thanks a lot.